Welcome to our implementation project presentation for the topic of traffic analysis and use of data analytics in cybersecurity, created by Alina Kraus, Shelley David Ashvili, and Shannon Soulard for the course CNT4403. Here is a more in-depth look at our team members along with their contributions to this project. We formed a group of 3 women, all majoring in computer science. First, we have Alina Kraus, who is our team leader for this project. Alina's responsibilities for this project involve data capturing for the machine learning models, DOS simulation, and assisting with the machine learning process. Next, we have Shannon Soulard, whose main responsibilities included the DOS simulation and setting up the isolated environment for the DOS attack. Finally, we have Shelley David Ashvili, who is responsible for the machine learning implementation that our group chose to go forward with. During this presentation, we will discuss the following: the problem and our contributions, some background on our topic as a whole, our machine learning connection, how we trained our machine learning models, how we conducted a DOS attack simulation to capture packet information, how we used that packet information to train the models again, and finally, some concluding remarks about the project. The main problem we decided to focus on for our implementation revolves around the idea of using traffic analysis and data analytics to categorize network traffic as either malicious or benign. In our approach, we decided to use machine learning to classify network packets based on an existing dataset. By doing this, we can create a baseline for comparison against the next part of our implementation plan, which was to apply the same model architectures to our own dataset. To create our own dataset, we needed to set up an isolated environment in which we could capture packet information. Network traffic analysis is a method of monitoring network availability and activity to identify performance issues and/or for discovering security problems. Network traffic analysis (NTA) solutions allow network administrators to collect data on the traffic that flows through a network, which focuses on all communications, including TCP and IP-style packets. A packet is the unit of data routed between an origin and a destination on the Internet. Packets contain control information and the payload, which is user data. The control information provides data for delivering the payload. A denial of service attack is exactly what it sounds like: the attacker denying the intended user from requesting a legitimate service. Affected services may include email, websites, online accounts, for example banking, or other services that rely on the affected computer or network. This is done by sending multiple requests to a resource in an attempt to overload the server with excessive traffic, which results in denying legitimate requests. A DOS attack can either crash the service completely or flood the service and make it unavailable.
Before discussing our implementation, we wanted to clarify some of the terminology that is going to be used when referencing our machine learning connection, as we understand that not everyone might have experience with artificial intelligence. A neural network is a type of algorithm designed to recognize patterns within a dataset. Machine learning models are trained on a dataset with a given goal in mind. For example, classification of data, which is what we used for our implementation. An epoch indicates the number of passes a model will make through a specific number of training examples, aka a batch size. Optimizers are used to change the attributes of a neural network to reduce loss. Loss functions measure how far an estimated value is from its true value. A layer applies to a collection of nodes that operate together within a network. It is something the data passes through. Parameters are variables that are tuned to increase the model's accuracy. Lastly, dropout is a technique where randomly selected neurons are ignored during training in order to combat overfitting. In order to evaluate how well our models performed, we use the following metrics to measure its success at classifying our data. Accuracy describes the fraction of predictions our model got right. Precision is the number of true positives, that is, correctly predicted positive values, divided by the total number of positive predictions. Recall is how many of the true positives were found by the model. F1 is the weighted average of precision and recall. AUC, or area under the curve, is the measure of the ability of the classifier to distinguish between classes. Finally, loss is the prediction error of a neural network.
The existing literature shows a variety of non-machine learning based methods and also machine learning based methods. The non-machine learning based methods commonly use something like a Python script to monitor the traffic and then detect if there was an attack or if it was just malicious traffic. In terms of supervised machine learning, there's papers that implement traditional machine learning techniques such as random forest, k-nearest neighbors, support vector machines, and then deep learning models are also commonly used, such as reference 4 that tried CNN and LSTMs. And then for unsupervised machine learning, clustering-based techniques are commonly used, sometimes combined with other techniques like autoencoders. The paper we chose to reference and replicate for our implementation used the UNSW NB15 dataset, which had features that we could closely replicate with some data packet capturing tools. So that was a good reference point from that perspective. And they also used 2 MLP models and 1 recurrent neural network model. And the MLP models were fairly complex, so we wanted to experiment with that and see if a more simple model could perform better or just as good. And for the implementation, we replicated just those 2 MLP models.
Our project consisted of 4 main components. The first was the machine learning models, which we implemented using Python and paired with libraries such as NumPy, which is used for scientific computations, Pandas for the data analysis, Matplot for displaying graphs, Keras in order to create the artificial neural network, and TensorFlow for training and inferences related to the neural network. The next main component was the data capturing software. In this case, we used Wireshark. The third component consists of setting up an isolated environment using a disconnected router and several connected devices. Lastly, the final component revolved around simulating a DOS attack using bash scripting and a CLI ping tool, which we felt should not be explicitly disclosed for safety and security reasons. Our implementation utilizes machine learning to categorize network traffic as either malicious or benign. This model has the potential to monitor real traffic over a network to determine when a DOS attack is occurring and could feasibly alert network administrators of suspicious activity. The goal for this project was to train our machine learning models on an existing dataset in order to create a baseline for comparison. We then later applied the same model architectures to our own capture data in order to draw meaningful comparisons and conclusions.
The UNSW MB15 dataset that we used for our implementation contained around 100 gigabytes of raw network traffic with normal benign traffic and also 9 different types of attacks, which included fuzzers, analysis, DOS, worms, and around 49 features. For the implementation, we narrowed down the dataset to only consider DOS attacks versus normal traffic, and we also narrowed down some of the features that we could most closely replicate with some packet capturing software.
In order to process the data within the UNSW NB15 dataset, our group used various Python libraries including NumPy and Pandas to execute the following steps. First, we imported the data from a CSV file and checked for missing values. All of the data points for the benign traffic were categorized as NaN, or not a number, so we changed the labels to 0. This way we could remove the true missing data. Next, we removed all the data that was not classified as either DOS or normal, and removed the columns that were not going to be used for the model. We also checked for any duplicated values and removed those occurrences. Finally, we noticed that the data was extremely unbalanced, so we extracted a smaller subset of the data points in order to balance the categories. As you can see from the graphs, before balancing, over 99% of the data points were benign. After balancing, this number reduced to 72%.
To prepare the UNSW MB15 data for the model, we had to do one-hot encoding for the categorical variables. We balanced the data because the ratio of normal traffic to DOS attacks was very, very off, which would make the performance very skewed. We separated the data into different subsets for training, validation, and testing. We did one-hot encoding on the labels as well, and then we also normalized the data with the min-max scaler. The first 2 models we used in the implementation were the multi-layer perceptron models from the paper that we referenced, and then we also proposed our own custom model that had a simpler architecture so we could compare. its performance and use the more complex models as a baseline, especially considering that we narrowed down the data a lot and made the problem more simple. Because of that, the ANN had one hidden layer with 850 nodes. The DNN had 3 hidden layers with 100 nodes each. And then for our custom model, we tried 2 hidden layers with 4 nodes each, and then a dropout of 40% in the middle. We evaluated all the models based on 5 metrics: accuracy, precision, recall, F1, and AUC scores. For the ANN and DNN and custom model that were trained on the UNSW NB15 dataset, they all were able to get 100% accuracy with no mistakes, and in terms of what the paper reported, it was very, very close with the full data set. So once we simplified the problem as expected, with it being more simple and having such deep models, they performed very great. These graphs show the progression of training and validation in terms of the accuracy and loss per epoch. For the literature models, the ANN and DNN, was able to reach very high accuracy very quickly and with pretty stable training. The custom model had slightly more overfitting shown and had a little less stable training, although the results were exactly the same at the end, perfect classification.
For this project, we decided to apply our machine learning architecture to our own dataset to see how it performs. To create our own dataset, we needed to set up an isolated environment in order to safely simulate a denial of service attack. To do this, we connected multiple devices to an access point that was disconnected from the internet. We also set up a packet capturing software that allows for traffic to be monitored within a network. Wireshark is a network protocol analyzer that enabled us to view the packets being sent over a network. In our implementation, we used Wireshark to capture benign or normal TCP packets over a wireless network. We also used Wireshark to capture our simulated DOS attack data within our isolated environment. These are the features we were able to capture using Wireshark. Time describes the timestamp of the packet. Source IP and port denote the address where the packet is coming from. Similarly, the destination IP and port show where the packet is going. The protocol is the specific internet convention used to transfer the packet. The length is the count of bytes that were captured for a particular packet. TTL, which is time to live, is the amount of time or hops that a packet is said to exist inside a network before being discarded by the router. The sequence number is a counter used to keep track of every byte sent outward by a host, and the acknowledgement number is a counter to keep track of every byte that has been received. The next sequence number is the next expected sequence number calculated using the last seen sequence number plus the segment length. Window size describes how much buffer space is available for receiving packets. Lastly, flags show what the sending TCP entity wants the receiving TCP entity to do. For the machine learning model, we did not include the time or IP numbers, as those mainly serve as identification features and would not be useful. To simulate our DOS attack, we set up an isolated environment. This was done using an old router disconnected from the internet. The router served as an access point that we connected 2 devices to. One device was used to capture traffic data via Wireshark, while the other device was used to send hundreds of thousands of packets over the network. The type of attack that we attempted to simulate in our isolated environment is a SYN flood attack. TCP SYN flood, aka SYN flood, is a type of denial of service attack that exploits part of the normal TCP through a handshake to consume resources on the targeted server and render it unresponsive. To randomize the data as much as possible, we created 5 different bash scripts. Each bash script used an open source packet generator to flood 10,000 packets with random lengths, random source addresses, and random time to live values. Within each of the scripts, 1 out of 5 possible destination ports was specified. These 5 ports were the most common ports being used within our normal data. To run the bash scripts, we used 15 terminal windows within the same device to simultaneously run each of the scripts 3 times. This essentially created 15 types of random packets. Why only 15 types? Because randomizing every packet greatly slowed down the rate of packet sending, to the point where it was no longer a DOS attack. It was necessary to send as many random packets as possible without slowing down the rate of packet sending. Randomized data was necessary in order for the machine learning model to make more meaningful connections about the data in order to classify it. Here we can see a breakdown of how the DOS attack affected the receiving device. In our simulation, when the attacking device was connected directly to the router via Ethernet, the receiving device experienced an average reception speed of 300 megabits per second. When connected wirelessly to the router, this number reduced to 200 megabits per second. Statistically, in 2021, the average DOS transmitted data at a rate of 150 megabits per second. In 2020, that number was 315 megabits per second. Overall, the receiving device experienced severe slowdowns, specifically when using Wireshark. In this video, we will show you a simplified version of how we simulated and captured data using Wireshark and command line interface tools.
This is our isolated environment setup. As you can see, we have two devices connected to a router. This router is disconnected from the internet and is instead serving as an access point for each of the devices. This first computer is running Wireshark and is capturing the packets being sent over the network, over the router. And this computer is being used to send the DOS attack. We are running a simplified version of the terminal command just to show how it works. And as you can see, as soon as we run the command, we see the types of packets being sent over the network has changed, and they are going at an extremely fast rate.
The final capture results from the simulation resulted in millions of packet dissections. In order to closer match our baseline dataset, we extracted a smaller subset of the data, ultimately ending up with a dataset that consisted of 69.4% normal traffic and 30.5% DOS. Note that these numbers closely match the percentages used for our balanced version of the UNSW NB15 dataset, which allows us to draw more meaningful comparisons and conclusions about the data we captured and the model we constructed.
Similar to the UNSW NB15 dataset, all the three models, when trained on the simulated data, had very high accuracy, and the custom model in this case had very, very comparable performance, just off by a small percentage amount, and it was able to get that close result and high accuracy with significantly less parameters when considering all the five evaluation metrics that we looked at. The loss and accuracy curves for all the three models had a similar pattern that it did with the UNSW NB15 data. For the literature models, since they were more complex, the data was able to get 100% accuracy fairly quickly and had pretty stable training, and then the custom model had slightly bumpier curves, but still very close performance and very high accuracy with much less parameters. When looking at the custom model specifically for the UNSW NB15 dataset and also the simulated data, we were able to see still very similar performance in terms of the raw numbers, and also the loss and accuracy curves were very similar. So that data set proved to be a very good baseline to compare to the data that we were able to simulate and capture. And the model also was able to perform well on both data sets. So some concluding remarks and some summaries of our findings that we noticed throughout the implementation. The biggest thing we noticed in terms of the data, how we simplified it to include only DOS attacks, we noticed that it greatly simplified the data itself and allowed the simpler model to perform just as good as the deep model. And in practice, or in real-time applications for real-time intrusion detection systems, using a shallow, more simple model could be more beneficial, since it can run faster and perform more effectively and efficiently than a much more complex model. And based on the performance of the models, using the existing data set that we referenced and our own data set, we concluded that the model architectures are pretty efficient with complex and simplified features. So features that are more easily capturable over network could still be used for intrusion detection systems with good performance.
Some of the main challenges we faced included randomizing the packet data for the DOS simulation, setting up an isolated environment, and overcoming data inconsistencies within the UNSW NB15 dataset. To randomize the packet data, we ended up using the aforementioned bash scripting technique to inject random number values into the CLI command. Setting up the isolated environment required us to seek out guidance and equipment from our peers, including obtaining and using the disconnected router. We had to sign in to the router's UI settings panel in order to disable the built-in DOS protection and other security features. Simplifying the UNSW NB15 dataset required us to apply a lot of data preprocessing techniques in order to obtain a usable subset. Overall, our team was able to carry out our original implementation plan with a few minor changes. Thank you for watching our presentation. We hope that you enjoyed. Questions, comments, and suggestions are welcome and encouraged. You can contact any of our group members using the emails listed here.